Alright, so now we're going to do, this is a pretty bread and butter type question for calculus, is to find the equation of the tangent line to a certain graph at a certain point. And it'll be really helpful if you can see a picture of what you're working with. It's not really necessary. But this is, you know, because you've memorized the basic graphs, what the square root of x looks like, right? Remember the square root of x looks kind of like that. And what is the plus 1 done? Well, now negative 1 is going to be sort of like the origin was before. So it's going to come out like this, all right? And what we want to know is what is the equation for the tangent line here at the point 0, 1 that's on the curve. And the tangent line is going to look like this. So it'll be sort of that line. Alright, so let's do it as a limit first, and then we will try to do it using our shortcut method. So, alright, so what we really want to know here is the slope of the line, because that's the only thing we don't know. You know, the point slope form of a line gives us a way to find the equation for a line if you know a point on the line and the slope. And we already know the point on the line, right? The point on the line is 0, 1, so this is just y minus 1 equals m times x minus 0, so just mx. So this line is y equals mx plus 1, and the only question is what the heck is m? And because of the meaning of the derivative, this is just f prime of 0 times x plus 1, okay? That's because one way to understand what the derivative is you put in a value and the derivative spits out the slope of the tangent line to the original function at that value, right? Okay, so let's go to the definition of the derivative. So what should f prime of 0 be? It's going to be the limit as h goes to 0 of f of 0 plus h is h minus f of 0. And alright, so here I've got h on the bottom. Now that's just the definition, and you know it has a geometric interpretation that we've been through in class. A lot like the way we moved b over to b3 in the example where we studied average rate of change. So let's do it. So you start with the abstract nonsense. Now you start using what the function actually is. So this is going to be the limit as h goes to 0 of the square root of h plus 1. And this is minus the square root of 1, which is 1. Right? Okay. So let's just keep going. So I can make it a little bit simpler because I know the square root of 1 is 1. 1 to any power is 1, by the way. And so we'll go square root of h plus 1 minus 1 over h. Now, you can't just plug in 0, because if you plug in 0, you get 0 over 0. And the way you do a problem like this is to rationalize the numerator, and I think we practiced that once, right, in the algebra review. So I'm going to rationalize the numerator. Actually, I guess we've rationalized the denominator in that example, but we're going to rationalize the numerator by using the difference of squares trick. And wow, the difference of squares has come up on like every single question on the practice exam. Maybe that's an important thing to know. And I didn't even plan it like that. It just naturally happened. Alright. So now I'm going to multiply this n. It's really easy because I can use the difference of squares formula, and for that reason I know that this is really h plus 1 minus 1 on top, and on the bottom I have h times all that stuff. Square root of h plus 1, and so on top I have the limit as h goes to 0. The 1's cancel. Yeah, you can probably tell from my voice I've kind of checked out at this point. So we're just doing algebraic work. There's a miracle that's happened that always happens, which is everything that doesn't have a factor of h cancels out on top, and then you can strike them out like this, and that after you make that cancellation, then it becomes possible to plug in, so that happens every single time. So now we want to know the limit as h goes to 0, and down here now we still have the square root of h plus 1 plus 1. Alright, and now there's no reason not to plug in, so when we cancel these h's we kind of defuse the bomb or whatever. So now we just have 1 over 2, because square root of 1 plus 1. Right, so the answer is 1/2. And now if we come back up here, right, we were almost done with this problem before we even started. We wanted to find the equation of the tangent line, and the only thing that was missing was the slope, but now we know the slope. And so the final answer to the question is the tangent line is the line described by 1/2 x plus 1. Alright, so now let's try to do it using the secret formula. So even if you are sort of on a test question forbidden from using the fast way to do these things, you can still use it to check your answer. So this is y equals x plus 1 to the 1/2 power. Now I want to caution you. I'm gonna pretend like this is just the variable x, right? By just bringing down the 1/2 and making this, sorry, there's plus 1 there. Take 1 away, it becomes minus 1/2. And it works in this case, but the reason it works is because the stuff inside the parentheses is so simple. And when we get a little bit further along, you'll learn how to deal with other cases where the stuff inside is more complicated. But because this is, because the derivative of the inside is 1, it doesn't make any difference in this particular case. So we're just using this to check our answer. And what are we supposed to do at this point? We want to plug in 0, right? Because this is y prime. And so what is y prime of 0? It's 1/2 times 1 to the minus 1/2, and 1 to any power is 1, so this is just 1/2. Alright, so it agrees. Same answer both ways, looks good. Problem is done.